So welcome to today's lecture on systems and algorithms for autonomous vehicles. So we're going to start the section on reinforcement learning. So when we play, there are a few short lectures by Carla from last year, from 1 to 4. So I hope you can watch them. Yeah, so these lectures are very useful for as introduction to the basic concepts. So for the Lab3, we have uploaded the lab to my GitHub. So it's based on a highway driving scenario. So I will explain this lab in more detail later today. So let's first briefly review some materials from last week, the planning lecture. So in planning, there was, I discussed the behavior planning, the mid-level planning, just after route planning and before motion planning. So there was one place where you use a finite state machine to model the intersection scenario. So stop, track speed, decelerate to stop, and follow leader. So you can make it a hierarchical state machine. Yeah, so Carla, I mentioned your videos in the media, in the email play media.
Yeah, if someone had some questions, they are free to ask me. And of course, if they have the questions on anything else related, of course. Yeah.
Yes, I think most students are watching the replay. So I guess only a few students attend the classes in real time.
Yeah, yeah.
So
So if you see this afterwards, you feel free to send questions in this topic.
Kalle,
Yep.
Your sound is very low.
Yeah. Let's see. Now I hope it's better.
Much better.
Yeah, I had some bad headset, so I have to put it on maximum. So anyhow, for those of you who watch this afterwards, you're still very welcome to call me and we can have a meeting on Zoom or email or forum discussions and so on. So I think some was are much more detailed and good to practical use. And my lessons are a little bit more up in the sky, so to say, without so much details, but more like my thought was to get a general understanding and then dig deep into these details, which is very good as well. So these are more like how to use it, when to use it, and so on. And Professor Songwa has good lessons for how to actually calculate those things. So I think they complement each other quite well, or I hope so.
yeah, maybe we can play it sometime later.
Yeah, absolutely. And now I'm working with Lab3, so I'm testing a little bit now. So I hope we have it ready.
Yeah, I'll discuss Lab3 in detail today.
Yeah, that's good. Perfect.
Yes.
So I solve it myself, so I can be of good help, hopefully, if someone gets stuck into something.
Sure. Yes. Yes. It's always a good idea to go through the process in case some small detailed thing gets difficult.
Yeah, I also installed this Git software to use that. That was useful also.
Yes. So in last lecture, the hierarchical finite state machine, you may transition from an intersection scenario with FSM inside to a drive line scenario, which is a different finite state machine. They just happen to have the same set of states in the figure, but they should have different transitions, trigger conditions and transitions within each scenario. So I added a slide to make it more clear that you may, in fact, have different FSMs within each hierarchical state. So you may have intersection scenario, drive line scenario, and multi-line scenario, where you have additional state of merge in addition to the 4 original states. So just to make things more clear. And for the part on responsibility sensitive safety, so let's briefly review it. So the idea is to formalize human notions of safe driving into verifiable model to clearly define, clearly assign blame and responsibility in case of accidents. So in fact, it's a very important matter from a legal perspective. So if an AV is involved in an accident, who's responsible? I mean, if it's a L2 AV like a Tesla, the driver is always responsible. But in the future, with higher levels of automation, should the AV manufacturer be responsible, or should the driver be partly responsible? So I mean, it's very hard to say. So by having these RSS rules in place and programmed into the planner of the AV can present a legal case in the court that this particular accident is not my fault. So then it's very useful, very helpful for the AV companies. That's why this is becoming industry standard, because AV companies do need this kind of clearly defined rules in terms of whose responsibility it is in case of accidents. So 4 rules, I explained the first one in detail. Do not hit the car in front by keeping a safe longitudinal distance. Do not cut in recklessly with a safe lateral distance. Right away is given, not taken. Be careful in areas of limited visibility. And if you can avoid a crash without causing another, you must. So this slide explains the formula for the safe longitudinal distance. So given the parameters of rho max, the maximum deceleration rate in the front vehicle, rho min, beta min, the minimum deceleration rate for the rear vehicle, and alpha max, the maximum acceleration rate for the rear vehicle, you may derive this formula, which says that this part corresponds to the this time interval when the front vehicle just started braking, but the rear vehicle is not aware of it yet due to response time delay, maybe sensing, maybe computing delay. So its response is not instantaneous. So on this part, so this part corresponds to this distance. That is when the rear vehicle has just become aware that the front vehicle is braking. It decelerates with deceleration rate beta min. So, and this term corresponds to the braking distance of the front vehicle with beta max. So the worst case is when the distance traveled by the rear vehicle minus the distance traveled by the front vehicle should be exactly equal to d min, the minimum distance to avoid collisions. So by having this formula in place, and also by knowledge of the parameters beta min, beta max, and alpha max, maybe from certification authorities, which is an industry-wide authority that determines these parameters, the vehicle can calculate a safe longitudinal distance. So, and by always keeping this safe distance, it is not responsible for any longitudinal crashes. So I added a small example in this slide. So here's a scenario where a car is occluded. So here's a car that's broken down on the road. It's parked on the road. There's a red car traveling in this direction. There's a yellow car. It's traveling in this direction. So the distance from the red to blue is unsafe. The distance from yellow to blue is unsafe. But the distance from yellow to red is safe. So taking into account all the alpha beta parameters, so in the formula here, so we have the parameters alpha max, beta min, and beta max, and also VR. VR is the rear vehicle speed. VR appears here. VF is the front vehicle speed. So the larger the VR, and the smaller the VF, the larger the D min, right? So if the front vehicle is very slow and rear vehicle is very fast, they will need to keep a larger minimum distance and vice versa. So for this scenario, the front car, the blue car is parked, it's broken down. So this guy has a speed of VF equals 0. So based on that formula, these two distances are both unsafe, from red to blue and from yellow to blue. But this from yellow to red is safe because both are traveling at a pretty high speed. So for the if the front car is a CF, since it's traveling fast, the distance from CR to CF satisfies a D min based on its speed, VF. But if we consider a blue car as CF, then it's very slow or stopped. So the distance from CR to CF may not satisfy dmin based on its speed VF prime. So so yellow car cannot see the blue car due to occlusion. So if the red car suddenly swerves to avoid collision like this, with the blue car, the yellow car may not have enough time to avoid collision with the blue car. So therefore, in this case, the yellow car should not be held responsible. So assume the worst case. So unless the existence of a car in a certain kinematic position is unreasonable, so in this case, the occluded blue car is very slow or stopped. It's an unreasonable situation. And yellow car will not be responsible for causing the accident. So otherwise, if you do not make this assumption, the yellow car will have to keep a very large longitudinal distance dmin from the front car, the red car, which makes rule 1 useless. So you never know if there's a blue car in front of the red car. So you should not make that assumption that the yellow car should keep a safe distance from the blue car. So it only needs to keep a safe distance from the red car. So the red car, on the other hand, can see the blue car and should either keep longitudinal distance dmin or change lanes according to RSS. So it should never suddenly swerve to avoid collision. So in this scenario, if the red car swerves in a very short distance and the yellow car hits the blue car, then yellow car is not responsible based on RSS. But the red car is responsible for the yellow car's accident because it did not keep a large enough dmin from the blue car. So that's just one example of assigning responsibility in case of an accident. So any questions?
Just to play devil's advocate, I mean, if a red car can avoid collision, why can't yellow one?
Oh, because let me see. So well, let me imagine a scenario that just as the red car crossed the lane and avoided the crash, there's a large truck blocking the way for the yellow car. So the yellow car can only brake, not swerve, right? Then because the dmin is violated, it may not brake in time to avoid hitting the blue car. So the rule number 1 is for the longitudinal safety. So if you only consider longitudinal movements, assuming that the yellow car cannot move sideways, then the red car will put the yellow car in a situation where dmin is violated, even though it's not yellow car's fault.
Just one more thing. At the time that when I took my driving license first time, there was talking like there was a rule that the driver is always responsible for the accident. If you actually if there is an accident, then it's you didn't adapt your driving way or speed to the conditions, so you couldn't just avoid the responsibility. I'm not sure whether this rule is formal rule, but that's how usually, like in the court, you would lose it anyhow. Almost any time.
Imagine a real life scenario. You're driving on the highway, and there's you're the yellow car. The front car is driving at the same speed as you, but suddenly it swerves, and suddenly you see the blue car, and you don't have enough time to respond. So that's possible, right? Then it's indeed the red car's fault, right?
Yeah, it's possible, but I'm just saying that in the practice in the court, usually you would lose because you didn't adapt your speed.
Yeah, but in this particular scenario, you wouldn't lose, assuming you have the full record of speed, all the cars' speeds. Yeah,
probably because in this case you have approved, you have formalized behavior, and then you can actually show the data from the computer. So, okay. Yeah.
Yes. Yes. Yeah. This is just another a kind of more concrete scenario for when RSS is useful. Otherwise, I mean, a lot of the traffic accidents are based on the traffic judges' decision, right? The judges make a decision based on available information, which may be incomplete. But with the future of automated vehicles all over the place, every vehicle has a detailed record of the speed, the trajectory. Then you can mathematically prove whose responsibility it is, enabled by the rules of RSS. So that's the whole point of RSS, is to eliminate the human judgment from the responsibility assignment. So it's not just the philosophy. Actually, it's a concrete software package in C++ that's open source. You can insert it into the planner module say in the Apollo, the open source framework for self-driving cars. Okay, so that's it for the planning lecture. So let me briefly introduce reinforcement learning. So the RL problem is to find the optimal policy given the reward function. So you have an environment, you have an agent, and the agent makes observations from the environment. Could be vision, could be LiDAR, radar, or other sensors. And it takes an action, AT, and gets a reward, RT, from the action. So the goal is to learn the optimal policy pi that mapped from state ST to action AT, parameterized by theta. The theta is typically a deep neural network in modern reinforcement learning. So that maximizes cumulative reward. That is sum of the reward over the future time horizon, 0 to t. Big T can be infinite or can be finite with a discount factor gamma, and you take expectation. So the reward function sometimes use a loss function, which is just a negative of the reward function. To minimizing loss is equivalent to maximizing reward. So reinforcement learning has its roots in optimal control, in the control field. In the control theorist terminology, you have the loss function, whereas in the RL terminology, you have the reward function. So we say that RL researchers are more optimistic than control theorists. So there are two types of model-based RL. One is model-based, one is model-free. So model-based, also called MDP planning. So given the Markov decision process, MDP is a function that maps from a state and action to the next state and reward. So given current state S and action A returns probability distribution of current reward R and next state as prime. So given this model, MDP is a model of the environment. So given the model, you can solve the MDP by planning with value iteration or policy iteration. to find the optimal action to do in each state. For model free IR, you can have a value-based or policy-based. So in this case, in value-free IR, you don't have the MDP of the physical environment. Instead, you learn the value function V or Q or policy function pi without learning the MDP. So the given state and action, you learn the V or Q, and then you take a argmax A of the Q value function to get the action to take in the value-based IR. Whereas in policy-based IR, you are more direct. You don't learn the value function. You directly learn the policy pi that maps from the state to an action. So model-free IR is the more widely applicable. All the major IR breakthroughs, for example, AlphaGo and AlphaZero and all the other. So they're mainly model-free IR, mainly because the physical environment model is so complex that it's not feasible to build a model offline. But for simpler problems, it's possible to build a model. If it's possible to build a model, then model-based IR can be much more sample efficient, much faster than model-free IR. But you don't have the luxury of having the model in most cases. So IR algorithms have many variants. So model-free and model-based, these are the two big categories. So for model-free, you have a value-based, which is a family of Q learning algorithms, DQN and hindsight experience replay and a few others. And you have policy-based with the policy gradient, A2C, PPO, TRPO, and so on. And you have a mixture of policy-based and value-based. That's the actor critique frameworks. And also you may have in model-based IR, you may learn the model with these methods. So learning the model in control theory terminology is called system identification. So you're trying to identify a model for the physical system. And also you're maybe given the model. So in terms of Venn diagram, you have model-based here, and you have a value-based and policy-based. And both are model-free algorithms. Their intersection is actor critique family of algorithms. That's the algorithms in the middle. Yes?
Yeah, I was curious also about, because many system identification is about linear systems. I think these are a little bit more powerful than linear systems, at least.
Yes, even for highly nonlinear systems, it's possible to perform system identification. For example, if your input is visual images from a camera, then you may predict the visual image in the next time step, given the current time step. So it's possible through deep learning, right? So for example, in visual servoing in robotics, when you push on some object, the object will move in the direction where you pushed. So given this, you may predict where the object is going to be in the next time instant. So that's an example of a model where given the state, the object's current position, the action, the push direction, you may infer the next state where the object is going to be and the reward, how close the object it is to the goal position. So that's one example of a model that's not a linear, that's highly nonlinear. It's predicting a entire scene. Indeed, for the highway environment driving scenario, there's a case study of a model-based IR. So this is the parking scenario. So this is model-based IR for parking, where they build a model of the environment, which is a linear model. X dot equals AX plus du. LTI, linear time invariant system, where XY, X is the state, and U is the control input of, yeah. So in this case, you can do a simple linear least squared fitting for finding these parameters of the LTI model. So in this case, because the perception is not really involved, you essentially are given the all the object positions as input. You bypass the difficult issue of perception, so you can have a simple linear model of the dynamics, and you can plan based on the dynamics.
Yeah, it's really very powerful, and I know the company Algorithms is now working a lot with RL, with Volvo and other companies. So this is really the future, I think, for complicated models. So yeah, enjoy.
Yes, yes. So a Markov decision process. Let me see how much I want to go. So I think I'll just yeah, stop at this slide. Okay. So a Markov decision process is a set of state and start state and a set of actions, and also a set of transitions and rewards. So this is the model, MDP model that we're talking about, and it's typically unknown for most cases. So a policy maps from states to actions, which is it can be deterministic policy A equals pi s, which defines a deterministic action A for state S, or a stochastic policy pi A given S, which defines the probability distribution over possible actions A for state S. So the Markov means that the next state only depends on the current state. So that is given a history of state actions, st at, st minus 1, at minus 1, and so on. The probability of the next state is the same as the probability of the next state given the current state, st and at. So that is all the previous states prior to the current state, these do not matter. So that is given the current state, the future and the past are independent. For example, for driving task, the current vehicle position X as the state does not satisfy the Markov property, since the next state depends on not only on X, the current position, but also on the current velocity X dot, acceleration X double dot. So but if we redefine the state as the vector position, velocity, and acceleration, then it satisfies the Markov property. So in autonomous driving, for example, NVIDIA's PilotNet. So NVIDIA PilotNet is a convolutional neural net, which is a feed-forward network with no memory. of the past. So it maps from the current snapshot of the front camera view to the steering angle. So the current camera view can be used as the state. But in some other works, in Waymo's ChauffeurNet, it uses past N video frames as a state to capture more dynamics. So for example, with a recurrent neural network. So if you only use the current camera view, strictly speaking, it does not satisfy the Markov property because the history, especially in the past 5 or 10 frames, may have a pretty large effect on the future state. So PilotNet has a limitation that it does not take into account any history at all. But by having some history, you can have a better performance.
I'll just comment also on that aspect, because if you have the old video frames in the current state, I guess it's still Markov.
Yes. In fact,
but the state will be huge. Yeah.
Yes. For the past, say N video frames, you may stack them together into a large input volume, right? So if you have 10 frames, each with 3 color channels, you stack them together into 30 channels as input to the CNN. But that's not what PilotNet did. The PilotNet was taking the current video frame as the current state. So maybe because it's the first end-to-end driving deep neural network that mapped from pixels to action. They are the pioneer. So I think they have some limitations in that. I mean, if they do stack multiple path frames together, I think it'll be more powerful, more performant.
Yeah, then you can calculate the derivative. I know the RL that solves Atari games usually stores 4 video frames, the last 4, to see if a game is moving and so on, and some parts of the game.
Yeah, okay.
A racket or a ball or something, so they can estimate movements. Yeah.
Yes. Yes. Yeah. The recent history can be very useful. Yes. So here's a small quiz. Here's a very small MDP with a single state and 2 possible actions, left and right. What are the valid policies? So the first one is that pi from state S, probability of going left is 50%, same as going right. So it's a uniform random policy. So at this state, you choose left or right with equal probability. Another policy is to always go left. Another policy is alternating between left and right. So if the previous action is left, the current action must be right, and vice versa. So from an MDP definition perspective, 3 is not a valid policy because it depends on the history of actions. Whereas to be a valid policy, the action must depend on the current state only. So 3 is not a valid MDP policy. However, we can redefine MDP's extended state to include the last action as part of it. So that is, the state is the current state S plus comma the last action as a tuple. Then 3 is a valid policy for the new MDP. So it all depends on your state definition. If your state includes enough history within it, then you can make it an MDP. So here's an example MDP with a green, 3 green states, and red are the actions. So you have 2 actions. Our agent taking action A in state S may get a different reward R and next state S prime, denoted as a state transition SA RS prime. So this is where the name of reinforcement learning algorithm called SARSA comes from. SAR, 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 and forever. So that's a trace of IR's state action reward. So is agent taking an action may get a different reward and end up in a different next state, denoted as the transition. So for example, from S1 taking action A0, you may have 10% chance of going back to S1, 70% chance of going to S0 and while getting a reward of 5, and 20% chance of going to state S2 with reward of 0. And also state transition SERS prime is atomic. So therefore you can remove all the red nodes and draw a single transition between the green nodes with the same meaning. So, but in general, we draw this state node and the action node separately, just to make things more clear. But you need to keep in mind that the SAR S prime transition is atomic. It's not a 2-step process. It's a single-step process. So for reward function, here's a driving scenario. Here's a vehicle had a state that is the poles, XY position, and the angle theta, and environment map. The action is a steering wheel, a brake, and acceleration. So one possible reward function is the weighted sum of the longitudinal velocity, that is v car cosine theta, that is the forward velocity to the right, and the cross-track error, the absolute value of the distance to the line center. So here is right at the line center, so the CTE is 0 for this case. So this is an example of a dense reward. That is, at every time step, you get a reward, as opposed to a sparse reward, only at the end of each episode. For example, playing chess or Go. So by maximizing this reward function, you make the car drive as fast as possible in the forward direction, while trying to stay close to the center of the line with the second term. So in our assignment, lab 2, we essentially only consider the cross-track error with the constant speed vehicle. So we did not really consider the heading of the vehicle in the assignment. So in fact, it's possible, if you want, to add this heading term to the assignment to always pointing forward, given constant speed. So pointing forward gives you the largest velocity in the forward direction. In fact, these two are related, right? So if you have a large theta, you're gonna oscillate around the center of the track, and your CT will be large. Yeah. So compare this with Triddle. So in fact, you may view Triddle as a higher algorithm, a policy gradient algorithm that learns the PID parameters with a sparse reward, where the cost function is a cumulative cross-track error computed at the end of each simulation episode as the sum of squares of CTEs for n time steps, actually average. It's not really cumulative, it's the average. Yeah. So it's a sparse reward because you're getting a feedback at the end of an episode. But this is a very crude reward signal. First, it only uses the relative size of the CTE as compared to the best error, not the numeric value. So if the error is less than best error, then the parameter DP is incremented. Otherwise, it's incremented less, it's decremented, and so on. So it's a very crude adjustment of the PID parameters based on the error. And also, cost function does not include the heading angle. So if the track is very long and irregular, we may make the reward denser to adjust PID parameters every k time steps instead of at the end of each episode. So it's a policy gradient method because you're adjusting the PID controller parameters, that is your control policy, directly without learning the value function or the physical environment, the model of the physical environment, right? So in the Triddle algorithm, we never learned any LTI model of the physical world. We don't have x dot equals ax plus bu equation for the physical environment. We don't care about if the physical environment is linear or nonlinear. We don't care how complex it is. We just try different PID parameters and see which one works best. So that's a policy gradient. So Amazon Deep Racer is this both a physical vehicle and an online virtual competition. So it's launched in 2018 for training AD algorithms with reinforcement learning. So the simulator can be trained with in Amazon cloud, but I think it gives you I think it's 10 hours of free time, and then afterwards you have to pay. So they hold competitions both online and in real world. So a 1/10 scale race car costs $349. So yeah, so that's one example of more of an education, project. So here's the reward function interface. So here's the track. This is the one of the tracks, and this is the blow up of the details of the track. So the vehicle first has a heading relative to the center of the lane, and cross-track error distance from the center. The track has a width and a few waypoints to reach, and steering angle of the steering wheel, and so on. So this is the kinematic parameters, and these are the parameters for writing the reward function. steering angle, progress, heading, center of left of center, distance from center, and so on. So here's a possible reward function. Define reward function as .1, 0.1 times the track width, 0.25 times track width, and 0.5 times track width. That's the three markers. And then if the distance from the center is less than or equal to marker 1, then it's very close to the center of the lane. You give it a high reward of 1. Otherwise, it falls between marker 1 and marker 2, then you give it a reward of 0.5. Otherwise, if it falls within marker 2 and marker 3, then it gives it a reward of 0.1. And if it falls outside of marker 3, then it's pretty far from the center, so you give it a very low reward. So steering ABS steering threshold is 15. So if the steering is higher than the threshold, the steering angle is too high, then you give it, you reduce the reward by multiplying for 0.8. So you're trying to keep the car steering forward. So if you remember the kinematic bicycle model, the steering angle controls the heading with a formula we discussed before. So they're different, right? Steering angle is different from the heading of the car, but one controls the other. So the agent directly controls the steering angle, which indirectly controls the heading. So we are using the steering angle to kind of approximate the heading. So if you're going forward, your steering should be 0. If you're always steering left and right, then it's likely that your heading angle is going to be large. So there's this is a very simple reward function. You may see a larger, more complex reward function for the AWS Racer project. So you may have progress, take the waypoint, the next point to reach, and speed, with different speeds, higher speed gets you more reward. And the marker is the distance from the line center. And the closer to the line center, you get more reward. And so on. So as you can see, reward function is a very difficult specification. So many IR projects turn into reward engineering projects. That is, even though you are not handwriting the algorithms, you are using deep learning, but there's one part that's handcrafted. That's a reward function.
I can mention I had a silly reward function because I had reward. If you stay on the road, you'll get a reward. If you're running out of the road, you get 0. But the problem is after 4 hours training, it found out that the best way to run this car is to stay still because they get through all the times.
Yes, you have to add the reward for speed.
Yeah.
Yes.
So I was surprised that it was smarter than me. Maybe not a surprise, but anyhow.
Yes. Okay. So MDP projects a search tree starting from each state. So both environment and policy may be stochastic. So that is policy mapping from state to action. It's a probability distribution over actions from state S. Typically in deep learning, you use a softmax to get a vector of probabilities. So after taking an action, you go into the next state S prime, which is again probabilistic. With a probability distribution over reward and next states. So from a perspective of an agent, you choose an action probabilistically based on your current state, maybe 80% chance going forward, 20% chance turning left. That's one example. And then after you take the action, the environment may be not deterministic, maybe because the wheel of the robot is slippery. Maybe there's a strong wind suddenly. Some physical disturbances that makes the next state not deterministic. So it's like a game between the agent and the environment. Agent takes a non-deterministic action, environment responds non-deterministically. So how do you prevent infinite rewards? So what if the game lasts forever? So the one approach is to have a finite horizon. That is to limit the search tree depths, terminate episodes after fixed t time steps. For example, life is a finite horizon game. Imagine that humans have eternal life. Then your reward structure would be very different, right? You wouldn't be pushed to finish your PhD or get a good job or get children or do anything. You think that you have infinite time, you can do it always later, right? So because you have this finite horizon constraint, some things become more prioritized. So that's one approach. Yeah, so here's an analogy of a non-stationary policy. So if you know you're going to die next month, you're likely to take very different actions today than if you will, you will die 50 years from now. So for another approach is discounting. Use a discount factor gamma, which is less than 1. So future rewards are less valuable, just like money. Money depreciates its value due to inflation. So the money 50 years from now is going to be worth a lot less than the same amount of money today. So a smaller gamma means a smaller horizon, shorter term focus, and vice versa. So observing state is a terminal state that is guaranteed that for every policy, a terminal state will eventually be reached. Yeah. So discounting. So in terms of the MDP search tree, every time we descend the level, we multiply the discount once. So think of 1 minus gamma as the chance of ending the process at every time step. So at every time step, you have the option of ending the game with 1 minus gamma probability, and also gamma probability of continuing. For example, if gamma is 0.5, then you get a sequence of rewards 1, 2, 3. The total reward is 1 times 1, that is the current state has no discount, and 2 times 0.5, discount at 50%, and 3 times 0.25, discount at 0.5 squared. So the total reward is less than the reward sequence of 3, 2, 1. So if you have a chance of making $10,000 this year, $20,000 next year, and $30,000 the next year, then the total amount of total value to you is less than if you can make $30,000 this year, 20 next year, and 10 next year. So here's an example of discounting. So you have a one-dimensional grid. Actions are east, west, and exit. The exit is only available in the E state, exit state. Transitions are deterministic. So if you have no discount factor, gamma equal 1, then the optimal policy is to always move left. That is going west. So because in the state A, you have a reward, large reward of 10. Then you can get this reward of 10 times gamma cubed in the worst case. So the reward is larger than going east, which gives you a reward of 1. For gamma is equals 0.1, then optimal reward is like this. At this particular state, if you're going west, then you get a total reward of 0.01 from gamma cubed times 10. If you're going right, you have the reward of 0.1 times 1, which is equal to 0.1. So the optimal action is going right in state D. So for which gamma are west and east equally good in state D, you can do the math and get gamma equals 1 over square root of 10. That is, at this point, if you go west, you get a reward of this, gamma cubed times 10. If you go east, you get a reward of gamma times 1. So when they're equal, then you have the equal reward going left or right. So here's the big picture. You may have a prediction problem, that is given a state, you predict the value function, or you may have a control problem, that is given the state, you're computing a policy that maps into an action. For the known MDP case, you have different algorithms. Policy evaluation is for predicting the value function. Policy iteration and the value iteration, and also Q value iteration are for control, for computing the optimal action. So let's stop here and take a break. When we come back, we will talk about the lab. So let's take a 10-minute break.
Yep, see you.
Okay. So in the lab sections, there's a link to the highway environment. So the environment has several environments: highway driving, merge scenario, roundabout, parking, intersection. So, and also a few agents, DQN network, DDPG, value iteration, Monte Carlo tree search. So it's actually a pretty popular framework used by many researchers in their publications. So he put a few examples on Colab. One is parking, one is trajectory planning on highway, another parking, and DQN. So, but these are more research oriented and not really suitable for beginners. So I have provided you with a very simple, no, where is my, okay, this one. Very simple agent based on DQN. So the agent, so let's look through the code. First, you pip install highway environment, and you do some a bunch of code for visualization. This is useful for running in Colab. And training. So our agents is a library, our library written by the author of highway-env. You can also use stable baselines, another popular library. So you load the environment, you can set some parameters of the environment. Here I set it to be a very simple one with 0 vehicles, that is except for the Eagle vehicle. There are no other vehicles on the road. And lanes is 2 lanes. Initial lane ID is 0. So the left lane is lane number 0. Right lane is number 1. So all the vehicles are started on lane 0. So here it shows the full configuration parameters for the environment, where I have my parameters in here. Lanes count is 2. And the vehicle count is 0. So all the others are default. Now here's the environment. 2 lane with a single vehicle on the left lane. And you may optionally run a tensor board for visualizing the progress of your training. And in the after training, during testing, you call evaluation norm episodes equals 3, and it'll record 3 videos for each one for each episode. So here's the 3 videos. So the video starting, if you look from the start, the vehicle starts from the left lane. It almost immediately goes into the right lane because of the reward structure, and just keeps in the right lane. And the next 2 episodes are the same. Starts from the left lane and goes into the right. So in this particular environment, highway-env, the vehicle is rewarded for reaching a high speed, staying on the rightmost lanes and avoiding collisions for highway driving. Some typo here. Your task is to add additional term to penalize changing lanes. So let me discuss this framework. This PowerPoint is available on my homepage, on my course page. In here. So there are two ways of making the environment. One is using the gem API, gem make. One is the other way I just showed you. So the yeah, so this one did not use gem. Yeah. So training the agent, you can use IR agents written by the author Laurent himself, or you can use OpenAI baselines or stable baselines 3, which is a very mature, well-tested set of IR algorithms, IR agents. So, but IR dash agents, this is Laurent's own library. It works, it's limited in scope. It doesn't have many of the sophisticated algorithms in baselines 3, but for DQN, it works well for our purpose. So a set of agents, including the planning, MDP planning, for value iteration and Monte Carlo tree search and so on, and safe planning, value-based DQN and FIT-Q iteration, and safe value-based. And also another alternative is stable baselines, based on OpenAI's baselines, but improved. So with the stable baselines API, you can write our agent in a few lines of code. For example, training a proximal policy gradient PPO agent, you can have gem make a card pull and model equals PPO2 with a multi-layer perceptron policy network, and train with 10,000 time steps, and then test. So a very short program for completing the PPO agent training. So here's the example provided for the parking. So the gem make a parking V0 and HER, hierarchical experience replay, a value-based learning algorithm, different from Q-learning, DQN, but this, they both are value-based IR, with a bunch of hyperparameters and train for 20,000 time steps and evaluation. So the highway environment, the vehicle drives on a straight highway with several lanes, and it's rewarded for reaching a high speed, staying on the rightmost lanes and avoiding collisions. So the environment is parameterized by configuration, defined as a config dictionary. You can also change the configuration parameters after environment creation. So the slide was a little problematic. I'll fix it. So observation .python file. This is the this defines the sensors for the vehicle. So it has several options listed on the right. So one of them is a grayscale observation. So it observes the image rendered by the simulator. That is a top-down view. That is this view in grayscale. The other is the kinematic observation. It observes the kinematics, that is the position and speed and heading angle. Yeah, position, speed, heading angle. But in fact, we don't care about heading angle too much. We care a lot about the position and speed because they determine if a collision is imminent. So of all nearby vehicles within the perception distance, defined as 6 times the maximum speed. So kinematic observation is a more powerful sensor. So essentially it assumes that there's a separate perception stage that has done all the hard work of deep learning, CNN, to deduce all the object positions from the camera or LiDAR or some other sensor. So now you're given all the positions and speeds of other vehicles. And your job is to train a policy network to make a decision of steering and braking and acceleration and so on. So another sensor is LiDAR observation. So it observes the direction and distance to obstacles within line of sight, just like a LiDAR sensor. So you may train different IR agents based on different sensors. For example, there's a agent called Stable Baselines highway-env. So this uses the grayscale observation sensor to map from the input image to the control decision. So this agent has a harder job because it must deduce the other vehicle's position and velocity from the grayscale observation. Whereas the vehicle given the kinematic observation has an easier job, which is our assumption in the lab. So action pi defines 2 types of actions. One is continuous, one is discrete. So action factory returns either a continuous action or discrete action. So continuous action space for throttle and or steering angle. So in the order throttle, comma steering. So acceleration range may be between -5 to 5 meters per second. And steering range may be minus pi over 4 to plus pi over 4 in radians. So another action type is discrete meta action. It's called meta action because the actions are actually commands for lower level controllers. All the actions are you have 5 actions. 0 is going to the left lane left. 1 is idle. That is that is stay at the current speed and current lane. Lane right is going to the right lane, faster and slower. So a typical agent has all the 5 actions available. But if you want, you can limit the agent to only perform longitudinal actions, slower, idle, and faster, or only perform lateral actions, lane left, idle, or lane right. So here's the init. So if longitudinal and lateral, return actions all. If only longitudinal, return longitudinal actions. If lateral, return lateral actions. So actions are called meta actions because they are actually changing the target lane and speed that are used as set points for the lower level controllers. Remember the hierarchy. From the planner, you issue command to the controller. So the Python class discrete meta action actually adds a layer on top of the continuous low-level controllers, so that the ego vehicle can automatically follow the road at a desired velocity. So here's the controller Python code. So these controllers act function takes a action as input issued by the planner, a high-level action to change the desired lane or speed, and then update the target lane, speed, and lane by performing longitudinal and lateral control. So a vehicle is piloted by 2 low-level controllers, allowing high-level actions such as cruise control and lane changes. Longitudinal controller is a speed controller. So if the action is faster, target speed is incremented by delta speed. If it's slower, it's decremented by delta speed. If it's lane right, the lateral controller is a heading controller cascaded with a lateral position controller. So
how this, sorry to interrupt, how this delta speed is measured?
It's a hyperparameter. You must set in the code.
Okay, thank you.
Yeah, I think it's not a tunable parameter. I think it's just hard coded.
All right. Thank you, Professor.
Yeah. So if it's lane right, you get the target line index. That is the right, the lane to the right, and check if it's reachable from the self-current lane. If it is reachable, then you set the target lane index to be equal to the desired target lane index, and similarly for lane left. So it's possible that it's not reachable from the current position. For example, if you are in the rightmost lane and you're trying to turn right, you get the lane right direction, then it's not possible. So then the self-target lane index will not be assigned. And actions are steering and acceleration. Acceleration may be negative or positive. So control algorithm is a P proportional control. We don't have the integral and derivative terms. So vehicle model is a dynamical bicycle model with tire friction and slipping. So we discussed the kinematic bicycle model where you map from the steering angle to the angular velocity and heading angle and so on. So this model adds dynamics on top of the kinematic model, even with tire friction. So it's a very detailed dynamic model. But we don't really care about these details. We only care at the planner level of the high level actions.
Excuse me?
Yes?
I can't remember that I've seen time anywhere. Where is there a time constraint or real time constraint?
So the whole system is driven by a clock tick. So every step is a clock tick. So at every step, you take a call act once, and you increment the speed and do something else. So yeah, there's an implicit global clock tick.
Okay, thank you.
So default configuration in this highway environment Python. So default configuration has a whole bunch of parameters. So observation is kinematics. That is, you observe the position and the velocity of all the other vehicles. Action is discrete meta action, not continuous. Lanes, 4 lanes, 50 vehicles. Control vehicles, that's your ego vehicle, there's only one. It's possible to have multiple controlled vehicles. Then the problem becomes a multi-agent learning problem. But here we have a single agent IR problem, so we have a single controlled vehicle. Initial lane ID is none, then the vehicles are initialized in random lanes. But you can set it to be a specific lane if you want. And the others, this reward, which I put on the slide, by default, every collision costs you -1 as a reward, and also terminates the episode. Right lane reward receives a 0.1 every time you move right 1 more lane. We'll see the example. So I think this particular sentence, linearly mapped to 0 for other lanes, is not very accurate. But I'll show you the formula. So a high-speed reward 0.4 is when the vehicle is driving at full speed, linearly mapped to 0 for lower speeds according to a configuration, reward speed range. So yeah, I think this author is a French person. I think he's not an native English speaker. It's not a very accurate description, but I think I know his meaning. So it means that from the 0.4 at the full speed, the upper bound of the speed range mapped all the way to 0 at the lower bound of the speed limit. And beyond the lower bound, even lower, you get 0. So a lane change reward is 0. That is, you don't care about a lane change. So that's what we want to change. Reward speed range is 20 to 30. So here's the reward function in highway-env.python file. So the explanation is here. So if crashed at collision reward -1, if crash collision reward, yeah, this line. This is the crash is a Boolean 0, 1 variable. you multiply it with the collision reward. And add right lane reward times the lane over max n length minus 1 and 1. So suppose so lane index is actually a array with 3 elements from, to, and ID. So this environment supports very complex road structures. So every lane has a starting point and end point, forming a graph in a roadmap. But for the lanes with the same from and to points, you may have different IDs for different lanes on the same road. So lane index 2 is the ID field. So if it's self-vehicle, you consider the target lane for the if you have a steering instruction. For other vehicles, consider the current lane. So neighbors contains all lanes in the same road. So this is this command: neighbors equals self road network all side lanes. So this returns all the lanes on the same road.
Excuse me?
Yes?
If you look at the first point, if crashed at collision, does it mean that the system will continue? Crash is not a catastrophic event, but we are continuing.
It is catastrophic, and it ends the episode. And it gives you a -1 reward.
Okay.
Yeah. So that's the final step in the episode. Yeah, so it's somewhere in the source code. I didn't put it on the slide that it ends the episode. The episode ends after either a collision or a fixed number of steps has elapsed. So suppose number of lanes is 2. If lane is 0, lane then it's the left lane. Then the right lane reward 0.1 times 0 over 1 is 0. If lane is 1, then it's the right lane. So you get a reward of 0.1. So this particular formula gives you higher reward for driving to the right. The more right you drive, the more reward you get. And it normalizes the reward to be within the range of 0 to 1 by dividing by this number. So this error map function is used to map from a range x interval x0, x1 to a y interval y0, y1. In this software package, they always map to 0, 1 type interval. So the formula is this. So if x is equal to x0, then it's equal to y0. If v is equal to x1, then it's equal to y1, right? So this particular formula maps from this x interval to 0, 1. It's a normalization step. So for high-speed reward, it multiplies 0.4 the high-speed reward value times the scaled speed. So scaled speed is defined as error map, linear map from the self-vehicle speed and the configuration reward speed range to 0, 1. So reward speed range in the configuration here is 20 to 30. So then this air map operator maps from the vehicle speed. If it's within 20 to 30, it scales to 0 to 1, and it adds a clip outside of the operator to clip it within 0 to 1. That is, if the vehicle speed does not fall into the range of 20 to 30, then this scale operation may return a value less than 0 or greater than 1. In that case, you clip it to be within 0 and 1. So the minimum is 0, maximum is 1. You cannot go beyond that range. So this is the this line here. This line, high speed reward. So finally, the total reward is the sum of the collision reward plus right lane reward plus high speed reward. And finally, you do a linear map into 0 and 1, normalize it. With the minimum reward of -1, the collision reward, a maximum reward of 0.1 plus 0.4. That is, you're driving in the right lane. At the same time, you're also traveling at high speed. So this is the minimum and a maximum range of the reward, because this is the reward for a single step. So it turns out that performing this normalization to the range 0, 1 has benefits during IR training. It's proved, it's shown in some paper.
Excuse me?
Yes?
How does this clipping operation works outside the range 20 to 30? Is it just like if it's over 30, it's 1, if it's lower than 20, it's 0, or is it some kind of the transformer?
Yes, exactly. So if it's 20, its linear map returns 0. If it's 30, returns 1. If it's 40, it returns something else, maybe 1.4 or something. So this is a linear map, returns this value, but we don't want anything above 1. So we do a clip after linear map.
Yeah. I forgot how it works. Now I remember. Yes, thank you.
Yeah, so in the code, so the scaled speed is the linear map operation to 0, 1, but afterwards clip further limits the scale speeds to 0 and 1. So so this is another environment, roundabout environment. The reward is defined differently. First, the default values are different. So right lane reward is 0 because we don't care about right lane. We just want to get through the roundabout. And lane change reward is a -0.05. So you shouldn't change lanes while in the roundabout. So the reward function says if crashed, collision reward, this line, return -1. And high speed reward times is a vehicle speed index over max speed index, count -1. So it's similar to the previous scaled speed, but using a discrete set of indices. I don't know why, but they just do it this way. The concept is the same, whether you use a continuous speed value or you use a set of indices. And lane change reward times lane change. So lane change is a Boolean value. 0, 1 is equal to action equals 0 or action equals 2. So if you look at the actions, faster, slower, lane right, lane left. So 0 is lane left, 2 is lane right. So these two actions cause the Boolean value lane change to be 1 and causing a lane change reward of minus 0.5. After you sum all of the rewards, you do a linear map to normalize into range 0, 1. So the range is the minimum is the collision reward plus lane change reward, which is minus 1.05, and high speed reward is the upper bound 0.2. So this is a different reward definition for a different environment. So the assignment says that the assignment says add a additional term to penalize changing lanes. Refer to a roundabout for reference. Yeah. And this is the create road, create vehicles function at system initialization time. So road.
Excuse me, one more question.
Sure.
Why do are we penalizing in both directions for lane change? I mean, even if it's correct direction.
Yes, even if you're changing to the right, you shouldn't change lanes too often on a highway, right? From a driver's common sense knowledge.
So I understand that, but it's more like it's more dangerous, and it's not. You should keep to the right, and then changing to the left should be more penalized than change to the right. So that's how.
Yes, that's a very good point. That's why, indeed, if you want to be accurate, you should do that. But this is more of a toy exercise. So in the original code model, the lane change reward is 0. In fact, in the formula, they don't even have the term lane change reward in here. So they don't care about lane change. In here, lane change reward is 0. In fact, I think it's reasonable. But this point of the point of the exercise is really to let you try to write some code yourself. So it may not be fully realistic. Yes.
I understand. Thank you. Thank you.
So a road is a set of road network, a set of point-to-point lanes. So, and create vehicles, create some random vehicles. So so for self-controlled vehicles, so I think this particular constructor create random here initializes the speed to be 25 and sets the initial lane ID from the config parameters. and then it appends this control vehicle to the list. In our case, we only have a single control vehicle, so the list consists of a single element. And then it adds the other vehicles based on the spacing and the vehicle density. So that's the highway environment. Then for agents, so in the source code repository, so he has the highway environment page. If you go upward, he has another repository for our agents. This is where he implemented a few common agents. So a few are shown here. So a very simple one is random.py. It simply samples from the action space randomly. It doesn't have any learning. It just randomly does any action. For the deep Q network agent, the act method so if it's exploration time, that is during training, you select from the exploration policy, could be epsilon greedy, could be some other policy, and take a step forward one time and get the values from the state action values and exploration policy update. Get the value from the state action values function and then update the exploration policy based on the values. And returns the exploration policy dot sample. Okay. So the environment and agent configs are defined. So environment dot JSON file is not useful. So the environment is defined in this highway-env data structure, and not really in the JSON file. So it's pretty much empty. But the agent DQN.json file is pretty useful. So the class is DQN agent from our agent library. The type is multi-layer perceptron, fully connected network with two hidden layers, each 256 neurons. And gamma, I think, is the learning rate for the training. And batch size is the batch gradient descent, mini batch size. Target update. This is when you update your target network every 50 steps instead of every step to keep the target network relatively stable during training. So exploration is epsilon greedy with these parameters. So here's the epsilon exploration factory method in abstract agent .python, because this is a common method for all the agents, not just for DQN. So it's defined in the abstract agent Python file. So it handles creation of exploration policies. Epsilon greedy is one, greedy is another, and the Boltzmann is another exploration strategy. So for epsilon greedy, suppose you have n actions, possible actions. That's the self action space dot n, the action space size for discrete actions. Then for each action, the probability of taking the action is epsilon over n. For the optimal action, it is epsilon over n plus 1 minus epsilon. So that is with 1 minus epsilon probability, you are choosing the optimal action. And with epsilon over n probability, you are choosing any one action, including the optimal action.
Could you please explain what's action space size is actually, what does it mean?
Oh, it means how many actions you have in the action space. For our system, we have the 5 actions.
Okay, so it's actually a number of possible.
Yes.
Okay. Yeah. Okay. Thank you.
Yes. So that's epsilon greedy exploration policy. So the reason that you're not greedy, that is, you're not always taking the optimal action, is because you want to perform exploration. That is, even though the action seems to be suboptimal, it may be it may bring you some high reward because of the unknown environment. So you should leave some epsilon chance of performing some random action. Otherwise, well, after you have finished the training, you can just be fully greedy. But during exploration, during training, you should be epsilon greedy. So these parameters, temperature and the final temperature, is annealing schedule for the epsilon. So the formula is this. Yeah, that's the code in here. So for if time over tau is 0, then epsilon is equal to big T, which is equal to 1.0 based on the default parameters. If it's infinity, epsilon equals final T. So the epsilon is gradually changed, annealed from 1 to 0.1. And the hyperparameter tau determines the speed of change from T to final T, final temperature. So default is temperature is 1, final temperature is 0.1, and tau is 5,000. So this means that initially the agent is performing random actions, fully random actions. And gradually, it's more and more preferring the optimal action as epsilon is reduced. And the rate of reducing from 1 to 0.1 is determined by the constant tau. So if you have a long training session, a few thousand, tens of thousands steps, then you should set tau to be large. But if you're only training for a few tens of steps, then you should set the tau to be small. It should match the total number of steps in your training schedule. So ideally, near the end of the training, the epsilon should be final t, should be 0.1. So this is the explanation of the highway environment. So for the specific steps, you should first fork the highway environment repository to your own GitHub. Then modify this Python file by adding the additional term for penalizing changing lanes. So if you're not familiar with GitHub, you may try this application for updating your GitHub from your desktop. And then in this line here, you replace the pip install highway environment to pip install git plus your own GitHub.
A question, Songwa. Will you
Sure.
provide the students with this notebook?
Yeah, it is right on my page.
Is it? I couldn't find it.
Oh, it's in South Labs and Lab3.
There's just a PowerPoint and then the readings.
Oh, it's on the previous link right here. This link.
On the Lab 2. Aha.
Yeah, it's all my labs are in here.
Okay.
Lab 2,
yeah.
Lab 3. Yeah.
Yeah. Good to know.
Yes. Yeah. So yeah.
You're assuming that we are going to work with what's called Colab.
No, I'm not assuming that. You can obviously work locally.
I mean, it's like everything is adapted, so it's easy to work with Colab. But how easy it? How you recommend? Do you recommend to work with Colab, or is it like easy to actually run it on own computer?
Well, I only tried a very simple environments. So the training time for me was very short. So Colab works fine for me. But as I said, more complex environments demand more training time, larger number of episodes. So don't make your environment more complex than necessary. So you may adjust some parameters to increase the chances of collision. The problem with Colab is that it kicks you off after some time. So I have a script on my page.
Yeah, I understand that. It's more like I prefer to work on my own computer, but my question was more like regarding whether it's not so easy to actually set up environments. For example, that's if it is easy, then I will most probably work on my computer.
It is actually quite easy. So running on Colab has a complication that you need some extra code for visualization, for TensorBoard and for visualizing show videos and so on. If you're running locally, these code wouldn't be necessary. But
well, it's not necessary if you're running Linux, but if you're running Windows, it doesn't work.
Okay. Yeah.
And I had some problems with the previous to set up, for instance, PyTorch for the GPUs. It's like it worked in Jupyter notebook, but not in the command line. So it's like I spent a lot of time to recompile, actually find out how it can be done. So it's like more I'm a little bit afraid of that I could end up in the same with that I need to spend a lot of time to just prepare for the working.
Yeah, but the script works quite okay directly.
It's okay. I mean, just was a question whether are we going? Is it expected that we will there can be some problems. So it's recommended to work with Colab, or it's just like it's pretty straightforward. So
it's pretty straightforward to work with Colab. As long as you can finish the training in a few hours. If you run it overnight, I'm not sure if it will be disconnected or not.
But Professor, at this page, you are showing that on Colab, we install that our GitHub code, right? Is it something?
Oh, GitHub is separate from Colab.
Yeah, but when we work on Colab, how can we get the GitHub things here? Because I understand that, okay, we on a local Linux machine, we download the code from GitHub and so on, but Colab and GitHub also integration can be performed, right?
Yeah, you do this. Pip
Okay,
install your GitHub address. Yeah.
After cloning the highway-env to your own user.
So this line installs the official highway environment by the author. If you comment out this line and use this line, then it uses your own environment.
So the basic idea is to clone the highway environment to your own GitHub and then edit and modify it to your wish, and then have this other blue line instead.
But you could actually, I believe, you can just import even from the original and then just change it on Colab.
You need to change the source code in the environment.
Yes, you need to modify the Python file. So you cannot modify it in his repository, right? So this guy is the original.
Yes, I understand, but it was some time ago that I worked with Colab, but if I remember it well, you could import some other actually GitHub repository and then change it and just save it, and then it will be saved on your just on new. Like you can choose just to save, and it will connect to your. If you connect to your GitHub, then it will just save it as a new project.
Yeah, but that's if it's only one file. Here you have to change several files.
Understand.
Yeah, I think another way is that you may copy the whole highway environment library to your Google Drive and install and do the pip install and import from there. I think that works, but this way I think is simpler.
Yeah, because the GitHub is public. If you have Google Drive, you have to connect to the Google Drive with security words and so on. And then you have to make it public also, so we can enjoy your code and study and so on. So it's easier if you use GitHub. And it's free. You can just create your own GitHub if you don't have one already.
So step one is a fork the highway environment repository to your own GitHub. Step two is to replace this pip install line with the pip install git plus HTTP your address. Step three is you train your agent for different values of lane change reward. So in the default parameters in my IPython notebook, I set these parameters. Single vehicle, 2 lanes, no reward for lane change. You may try different values of the lane change reward. Notice that it has to be negative. So the reason is that it has the linearization step, normalization to range of 0 and 1. So if you remember the highway reward, it has the minimum reward collision reward, if you add the lane change, the collision reward plus the lane change reward, two minus points forming the lower bound, and the two plus terms, right lane reward and high speed reward, form the upper bound. So if you give it a positive reward for lane change, and then the lower bound will exceed the upper bound, then this doesn't work anymore. So this error map step basically forces you to set the lane change reward to be negative.
And you don't want to encourage lane change anyhow, so it should be negative to do a lane
Yeah,
change.
I just thought it may be fun to to force your car to change
like a
lanes.
slalom car.
Yeah, but it doesn't work. Yeah.
But there is a step 2.5 also, that you need to change the highway environmental files to make it work, of course.
Yes. Yes.
2.5, step 2.5, actually write some code lines.
So makes the lane change reward very negative until you observe that the vehicle prefers collision to lane change. So submit your notebook and short description of the different configurations you have tried, at least 3 configurations, and your observations for each configuration. So notes are, first, do not make your environment too complex. So you may try to increase the vehicle density and reward speed range to increase the chances of collision, because the larger the reward speed range, the more different the vehicle speeds are, and the more higher chances of collision. And there are also some DQN parameters, typo, in the DQN JSON file. For example, discount factor, epsilon greedy parameters, you may tune. So if you get an error message, so actually this error message essentially says the local directory for the pip install for the git clone statement has been already occupied, so it'll fail. So actually this doesn't really matter. I later realized. So I'll update this. So just ignore this error message. So in this particular example, I set the training episode to be 10. Very short training episode. Because it's so simple, the scenario is so simple, right? But in fact, you see it changes from left to right lane. In fact, in some cases, it never changes lane. It stays in the left lane. If you train it for too few episodes, it's because the whole thing is random, right? It chooses a random exploration action at every step. There may well be a chance that it never tries the right turn action. Then it will never learn the right turn action, a change lane action. So a few times I saw this car just driving in the left lane forever. Don't be surprised if you are training for very short episodes. So I think the first thing you should do is to run my IPython notebook a few times with different vehicle count, and you know, initial lane I set to be 0. So that's because I wanted to see the lane change behavior from left to right. At least it's a sanity check, right? It should change lanes to the right.
One question.
Yes.
Is it necessary to use TensorBoard?
No, it's not. TensorBoard is optional. It's just for visualizing the progress. You can just comment out this line. It's just optional. Yeah.
Again, it's compatibility problem, so it's not working anymore for me because it's other kudos. So.
Okay. Yeah.
But here TensorBoard is running in Colab, yes. Mm.
Yes, I'm assuming that I will be working with my computer.
Yep. Mm.
Yeah, so this is the first time we give out this assignment, and I only tried a simple environment. So please let me know any issues you run into. We'll respond in the chat room. So this I think this may very well be the last lab. I set the due date to be 30th of May, with a possibility of extension if people can't finish it. I set a bonus lab question mark. So we'll see how this thing goes, and we'll decide if we want to give out a bonus lab for bonus points if everybody can finish lab 3 in time.
Yeah, when we discuss this, I have a question. Actually, it's related to course logistic. I missed at regular classes attending with you. But my question is, like you mentioned that 10 mark for lab 1, lab 2. I actually didn't submitted the lab 1 yet. In that case, what is the passing? How much is for the exam? Is it like 70 mark for exam, 30 marks for labs? I couldn't find a slide on that. I mean, if I'm like lab 1, I haven't submitted yet, but still I can pass the course. Do you mean what I'm saying? A clarification.
Oh, yes. So the plan was to have 4 labs, each worth 10 points initially. But it turns out the labs were not very straightforward. So people had a lot of difficulties. So we're thinking of reducing to 3 labs. And the point distribution should not be uniform. Lab 2 is pretty easy compared to lab 3. So lab 3 should be worth more points than lab 2. So I think the current plan is to have 60 points, 60% for the exam, and 40 points for the labs. And lab 3 should be worth 20 points.
Okay.
Yeah. And
yeah, passing mark for the course is 50 point, or how you define that?
Passing mark, as Carla should know, I think is typically 60, right?
Yeah, you decide. It depends. So 60 for just grade 3, and then you have grade 4 and 5. So it should be like 75 and 90 maybe for grade 5, but you can also have lower or higher. You decide yourself.
Oh, I see.
But there is a course plan maybe, which we have to look at if it's detailed there maybe.
So in lab 1, like those who couldn't submit, should I can see that it's still open. Can we submit? Can we, of course, maybe not full mark, but can we get some mark if we submit the lab 1 still submittable, or do you have anything else that, okay, it's now you cannot submit, you will not get any mark after 7th of May? Is it something rigid, concrete you have decided?
I think what he's asking is the final deadline for the labs.
Yeah, so that's the issue. We did not really anticipate any late submissions. So we didn't have a late policy set up.
Actually, at universities in Sweden, we get something like, okay, submit it on the first action, and otherwise you can submit it during your second chance in August. Something we have in Sweden, but I don't know, you have your own course policy, but I was thinking in case first attempt we couldn't submit. we submit some other lab, or maybe with some other extra task or some modified task, you give us second chance for the lab 1, for example, because it's high mark to pass, and then if you miss one lab, then it's hard to get the pass mark with the exam. And so the second chance could be lab 1 with some other task. I'm just wondering.
As I can see, Songo presented that. Please note 7th of May will be a hard deadline for lab 1.
Yes, I got that. But I was, you Kalle already know that we in Sweden, we usually get a second chance with maybe modified assignment or something like that.
Yeah, so usually that is, yeah, so it depends if Songo decide if this is obligatory. Then you fail the course if you haven't done all the labs. So I'm not sure they are all obligatory.
I mean, we have this lab and exam all together is an average for passing grade. As I understand, in that case, if we like somehow miss one lab, the deadline, and if we don't get the second lab submission, then actually someone can fail. But if we can get the second chance for the lab, like you can explain it to Zingo that we have that opportunity in Sweden, August submission.
Yeah, usually you have a second chance in August or something, then close to the re-exam to redo all the labs if you failed on them or something. So there is several years of chances to finish. But maybe this hard deadline, which he mentioned, is to get ready for this course ready in June or something. Then we will wait for August to collect the late students to do a second round of the course. Because as a teacher, you can't correct labs all the time. You have to kind of leave one.
Of course, you have so many other responsibilities. You have research, you have other classes. I totally agree. But I'm just wondering, because we don't see any information about second chance for lab 1 or something. And that's why I'm wondering, because I want to complete this course. That's why.
Yeah,
sorry.
That's right. So I will talk with Soba, so we will solve that. There is also
if I may say something.
Yeah.
It's like there are two different approaches. The one is that if the lab exam, I mean, it's like grade based, so you can't get more points than you need to actually submit lab that gives you some credits. Then should be like for the next time, because you can fail the exam, so when next opportunity for the exam, you should be able to actually even submit labs. But if it's just like it's mandatory to pass the labs, but it's not part of the exam, then it's like you just repeat different, you have different periods of the time for the submitting. So it's like in this case it's like both, but it's part of the exam. So which means that if you don't submit in time, but even if you do a re-exam, you never can reach the maximum points.
Yeah, you can decide that as a teacher that you only get like high points if you're in time, and then you get a little bit lower score for late in August or something. Yeah, or after May 7th. So there's different philosophies how to grade. Of course, you will encourage the students to send in time, but you don't want a lab in time, but which is very bad. So there is a lot of work to give feedback on very bad labs. So you want students to make a reasonable attempt also.
And well, it's ultimate goal is actually to learn, so to be not just like,
yeah, absolutely. And we are happy if you finish the course as well. So then the university gets money and you get your grade and so on. We are happy about that. So you should give the students some extra chances later on. But of course, as a teacher, yeah, we have to do with lab 1 and then lab 2 and lab 3. So it will be a mess if we have to do all the labs at the same time at the end. So there's
yeah, it's fine to get a re-exam time in August for lab 1, but I'm just thinking if we can get that deadline for this time submission. Maybe if with the re-exam, someone submit this lab 1 or a modified version of lab 1 suggested by you. But at least we get the second chance for the labs as well. That's my concern only.
Yeah. So I will talk with Songwa, or unless he knows already.
Yeah, I think we can, for those who choose the re-exam in August, I think we can give the students a second chance at the finishing the labs in August. But for those who choose to take the exam in 31st of May, I think you should finish the labs in the May or June in this time frame, based on the original deadlines.
Yeah, but then they have a second chance in August. Sometimes you can't do that, because if you send out the answer of lab 1 and 2, of course that will be too easy for those in August if they already have the answer. But we don't send out the answers.
Yeah, it's better if you don't send out the answer. If you keep the same assignment, maybe after August re-exam and everything is closed, then you can send out, up to you. But of course, it's up to you.
But that's unfair for students that have submitted the labs on time and they want to check their results. Can't you just do that, like the people that submit the labs after the hard deadline, they only get the pass grade, and then you can release the solution also? Because like in lab 2 for the PID, before you change the task 1, I had already done it, and it's totally fine. It's okay. But I mean, like, it's still, same thing happened in lab 1. So I think like some fairness it should be, like, it's not always like, yeah, but okay. Like, I would like to check my solution also, like before, for the August, for the start of next courses.
Okay.
Usually you get some bonus for being in time and doing extra stuff, and maybe get lower score in August or so, because you then had more time.
I don't care about the grades or the bonuses. I just like, I would just want to compare my solution. That's what I want to do.
In that case, it could be professor could suggest a solution for those who pass the assignments. Then they get the solution, only them. And they, of course, they have their own ethics. They will not submit with the classmates. That will be easier. In response to your feedback, maybe professors share with you. That could be one solution. That's my thinking only.
Well, for lab 1, we're not gonna give out the solution, because there are so many ways of doing lab 1. You can design your own CNN, you can use some other people's, you can do transfer learning. There are different ways, so there's no standard answer. For lab 2, yeah, there's an answer we can give out. For lab 3, in fact, the modifications you have to do in the coding is really trivial, just a few lines of code. The main thing is for you to explore, to try the experiments. So in that sense, the answer is not very valuable for lab 3.
Regarding lab 3, but you said that it's most difficult, it should carry 20 points or credits. So it's like...
yeah, so in the sense that the main difficulty is in the trying the different values of rewards and tuning some parameters and doing these things. So the modification of this Python file is pretty easy, actually. 3 lines.
That's exactly what I thought, that it's like, it seemed easy, and you said that it is very, it's like more difficult. So it's maybe it's most time consuming, but it doesn't seem like very difficult.
It's not so difficult, the coding part, but it might be difficult to understand what's happening and find what file to change and how. Not much writing, but it's difficult to find the place, maybe. You need to have an understanding of how this environments work and the agents work and so on.
Okay.
I think that's the reason for higher score. It's more complicated, but not much to write.
And just now I want to take opportunity to ask for the possible bonus lab. If you decide extra lab, what is it going to be deadline for that lab? Because it's if it 30th is for the third one, which date would be then for the fourth?
Oh, the deadline due dates are, you see, it's already overlapping. So the lab 2 is due on 17th, and lab 3 is due on the 30th. So the bonus, I may set it to be early June sometime.
Yeah.
Haven't decided yet.
So it will be past the exam, actually, not within exam.
Yeah, that's reasonable. So it could be worth, say, extra 10 points. That's above and beyond the 100.
Okay. So it's not. So you can, if you have a low, I mean, you can reach 100 even if you don't submit 4.
Yeah, that's the idea. That's why it's called a bonus.
Okay, thank you.
So yeah, for the lab policy, I think we should discuss a little bit and formalize in writing. So my idea right now is to apply a discounted grading for people who submit in August for the labs.
Okay, at least,
Yes.
yeah, submitted. Thank you.
About lab 2, can we take it today or should we postpone it until Wednesday?
Postpone? What do you mean?
Should I ask my question on Wednesday, or is it okay that I ask a question about lab 2 today? I see that we are 40 minutes after the lecture finish, and I don't want to take anybody's time more than necessary.
If it's a short question, you can ask.
No, so I was doing task 2, but I don't know how the images should be. If you go down, like for task 2, yeah. So that's the image you have when it doesn't work so well. So the images I have in the end for P, I, and D are not that good. So that's what I'm wondering. If I'm missing something, I can I share my screen with you? Is it okay?
Yeah, sure.
You have to stop sharing. Yeah. So yeah, so this is only the P controller, and that's the end result. I get it like this, right? And here is the PD, and in the end, here is the ID controller, right? It doesn't get as good as the one here, like in the end, but I'm using 10 speed at 10 and radius of 25. But is this, am I on the right path, or am I like in the whole totally wrong path?
I think it's reasonable that you may be able to control well with a PID controller, but maybe not with P or PD or yeah. And okay. Also, I think the problem is it should be a full round circle. Shouldn't be this shape.
You mean here, like in the end, or
yeah, in the
working?
End.
So I mean, yeah, sorry.
I said in the assignment is to change the track shape to a round circle.
True. But in the lab that you send it as a reference, you don't have a circle, you have a hyperbolical. So I changed it back. I assumed that that was not the case anymore. Or that was in task 1 that you were supposed to change the trajectory, but that's maybe I just missed that. Yeah, I probably missed that. But yeah, sure, I can change it back to a circle. It's not a big challenge for that. But
I see. I see what you mean. So
yeah,
task 2 should follow task 1. That was my point. Yeah.
Yeah, but I assume since you removed task 1 that we don't need to change it to a circle anymore. Because I had it a circle before, but yeah, should I change it back or what should I do?
No, the new task 1 says change the track shape to a round circle, and task 2 follows task 1 and should continue to be a circle.
Okay. Wait, the new instruction we got was that we don't need to do task 1, right?
Yeah.
We only do task 2. And
so the new task 1 is the original task 2.
Oh, have you updated?
I did many days ago.
I still use the first iteration of the lab instruction. So I have to look there. Okay, I should change that also because I was doing the first iteration. Should I could do the new one, right?
Yes.
Okay. Thank you.
Just for the record, I mean, you should. I think it should be fair if you follow the original one and it's correct. You shouldn't need to change it.
Yes, that's fine too. If you follow the original one, yes.
Okay, I'm confused. What should I do? Should I follow the original one, right?
I mean, to do the assignment based on the current new instruction, I think it doesn't involve too much extra work, right? You just change it to the circle, round circle, and then continue with the round circle in the next task. So yeah, do that.
Okay. Okay, I will do that then. Thank you very much.
Okay. So no more questions? Okay, that's great. We are way over time. So see you later.
Thank you for your extra time.
Yeah, bye.
Bye.